Continue from where we left last time. We were talking about parallel histogram computation, and now we will be talking about what to do if our data set is biased. By biased, I mean, let's say we have images where there's a lot of background, and because of that, the pixel values might be leaning towards towards 255 rather than towards 0. So there'll be a lot of pixels with a value, let's say 255. And if we use the previous kernel, there'll be a lot of contention in atomic updates and there'll be a lot of waiting. So the way to handle that is by using an accumulator or register variable per thread. So every time we iterate over the for each thread, every time we iterate over the pixels it is responsible for, we see if the previous pixel value is equal to the current pixel value. We just increment the cumulative variable, and if it is not, we then in that case we do an atomic add on the corresponding bucket. So this way we'll have a lot less atomic adds being executed uh, if if the same um, value is seen very often in the data set. And an alternate strategy could be, instead of using just one accumulator register variable per thread, if we have, let's say, 7 buckets, and why we have 7 buckets is because we have 26 alphabets, and each we classify each bucket as as consisting of 4 alphabets. So there'll be seal of 26 by 4, that is like 7 buckets. So we for each bucket we keep a accumulated register variable. uh, yeah, so we can not only in this way we can not only handle skewed data, we can also handle unskewed data, unbiased data, sorry. And yeah, but the con with this is we need more registers per thread. uh, but the pro is we have less contention in atomic adds. Yeah, now I want to discuss about the application of parallel histogram computation, an example. So let's say we have as input 1000 images, each of 1024 cross 1024 cross 3 dimensions. 3 is the number of channels, let's say RGB. And one way to do this would be to split the input into a grid of dimension 1000, 1, 3. So each block within the grid would be responsible for 1024 cross 1024 image, 1024 cross 1024 2D image. And let's say the block dimension is 32 cross 32. So the green block is a 32 cross 32 block, and each of the, let's say this thread, like the 0 comma 0 thread at 0 comma 0 location, would be responsible for the all the red values, right? So this so each thread would be responsible for 1024 divided by 32 into 1024 divided by 32. That is like what is it, 1024 by 32 is 32 cross 32. So each thread is responsible for 1024 values. Okay. Is responsible for 1024 32 cross 32 computations. So units of work. So coarsening factor for each thread is 32 cross 32. Yeah. Now we want to calculate for each pixel value. We need to see in this 1024 cross 1024 image how many pixels have that particular pixel value. So a naive strategy could be to store, so teeing off from the like the we were considering using seven um, register variables per thread, right? We just discussed that. So just extending from that, we can use 250, since we have 256 buckets here rather than just seven buckets in the alphabet case. So we can use 256 registers per thread, and each register will store the number of each register. Let's say register I would store the number of pixels in this 1024 cross 1024 image, which has the pixel value I. And in the worst case, let's say the whole image has value 0. In the worst case, the register 0 should contain the value 32 cross 32 minus 1, because we are following zero based indexing. And so each register can have a value in the range 0 to 32 cross 32 minus 1. An observation here is, although we use a int 32 variable for each register, the actual um, like the actual range we are using is not 32 bits. We are just using 10 bits, because each register can have a maximum value of 32 cross 32 minus 1, that is 2 power 10 minus 1. So we see that out of 32 bits, only 10 are being used, 22 are being wasted. So a better way might be, rather than using one whole register for storing the rather than using one whole register per pixel value, we can maybe share a register between various register values, various pixel values. So an example could be um, let's say, rather than making the grid dimension 1000 comma 1 comma 3, we make it 1000 comma 4 comma 3. So this way, the maximum value required, maximum value that each like pixel value, the maximum number of pixels in this 512 cross 512 image area, uh, 512 cross 512 image area 1024. Okay, so 512 comma 5 cross 512 is the image area, and 32 cross 32 is the block dimension. So the maximum number of pixels per thread that can have a given pixel value is this, which is 16, 16, 256. So each register 256, which is 8 bit. So if we were to use a full register for each pixel value, we would essentially be wasting 24 bits out of the 32 bits, because only 8 bits are useful. So the takeaway from this is, instead of using 256 registers, instead of using 256 registers, and where every register is responsible for each pixel value, we share one register uh, amongst 4 pixel values. So maybe the first register, the first 8 bits could count the number of pixel with value 0. The next 8 bits could count the number of pixels with value 1, and so on. And maybe like the register number ID 63, the first 8 bits of that register could calculate the number of pixels uh, in the image, in the 1024 cross 1024 image, in the 512 cross 512 image area, with the value 252, and so on. But I mean, one thing I would like to highlight here is, note that we could also use shared memory uh, here, and use atomic updates on that shared memory. So we could define a shared memory area of size 256, and each thread, whenever it comes across a value, let's say one thread comes across a value uh, 10, and another thread comes across a value 10, so we would have to use atomic add for each thread on this shared memory area. Although this is faster than doing atomic update on the global memory, I mean, although using atomic update on shared memory is faster than using atomic update on the global memory, but still it is it is far from optimal. So, but in practice, it should be we should try both the approaches. So this current approach that we're discussing, and also the shared memory approach, and see which gives a better result for the input data. Okay, now that we've discussed the second approach, alternate approach, extending this even further, rather than using a 512 cross 512 image area per block, we can use a 32 cross 32 image area per block. So the grid can be, instead of 1000 comma 4 comma 3, we can have 1000 comma 32 cross 32 comma 3 grid, and each block is 32 cross 32 cross 1. So each thread is responsible for just one pixel location. And if we were to use 256 registers per thread, each register would just have be a flag register, would just be a flag register, boolean flag. That is, does this, let's say the 0th register out of these 256 registers, if that is 1, that means that the current thread has the pixel value 0. Otherwise, that means the current thread does not have a pixel value 0. So, yeah, so I here explain here that, let's say if the register at position 150 is 1 and all the rest are zeros, that means the pixel that is corresponding to the current thread has a value of 150, pixel value of 150, intensity value of 150. So again, using a similar logic as before, rather than using 256 32-bit registers, we just use 8 registers. uh, yeah, we just use 8 registers because each bit of the 32-bit register can be used to store the information about the whether or not this pixel value is uh, like the current thread has that pixel value or not. And there are 256 possible pixel values, so we need 256 bits, but each register has 32 bits, so we need 8 registers to store the entire information per thread. Okay, now uh, once this is done, we imagine that we have stored 8, each thread has 8 registers, and after um, each thread has 32, oh sorry, each thread has 8 registers. Mm-hmm. Okay, so this is a 1024 cross 1024 image, and out of this is a 32 cross 32 block, right? And this is the entire so each block corresponds to this area in the image space. So now with 8 registers per thread, each thread like this, for example, this thread has 8 registers, this thread has 8 registers, this thread has 8 registers, and so on. Now we want to aggregate all of these block values into just 8 register values, so that the register values contain the uh, pixel number of pixel values in this 32 cross 32 image space. Okay, from so now we are going to aggregate results from a thread domain to block domain. And the next step in this, so this is the responsibility of the first kernel that we are discussing right now. And in the second kernel, we will go from block space to grid space. That will be the responsibility of kernel 2. We'll be discussing kernel 2 later. Currently, we are on kernel 1. So the way we do, so we'll call this as block reduction because we are essentially reducing the while computing the results of the entire block, we are essentially reducing the results of the block. So that's why we call it block reduction. And the way we do it efficiently is using intra-warp communication. CUDA provides intra-warp communication, which is very fast compared to normal like shared memory, even shared memory communication or normal reduction techniques. So the way we use that is each we know each block is a 32 cross 32 has 32 cross 32 threads, right? So the first 32 threads will make up warp 0, next 32 threads will make up warp 1, and so on. So in the first step, we'll do warp reduction for all these 32 warps. Okay, and we'll do this since we have 8 registers, we'll do this for all 8 registers. Like we'll maybe have a for loop for all 8 registers, or just uh, do this warp reduction 8 times. No, don't have a for loop, do this warp reduction 8 times separately for all the 8 registers. So after step 1 we'll have all these, let's say we are considering warp 0 now. So all the threads, all these 32 threads in warp 0 will have the same value, which is the sum of uh, all of these values reduced. So all of these will have the same value. We'll take the value, we'll make thread 0, so that is the thread which is at column 0. We'll make it responsible for putting its value into shared memory in the second step. In the third step, we'll upload this value from shared memory into the first row, into row 0. And the reason we do this is because we want because in the fourth step we want to reduce the warp 0. Like after step 2, each um, like each row, let's like this pixel, this pixel contains the reduced value of their individual rows, but we also want to reduce the sum across rows, right? Till now we have just reduced across columns. So to do that, we first place the data, the row reduced values into shared memory, load that value from shared memory uh, into the first row, and then do a warp reduction uh, on warp 0 to get the whole 32 cross 32 blocks result in this place. Like after reduction, all of these would have the same value. That is the result of the entire block. But we uh, take TID 0. We make it the responsibility of TID 0 to store this result. Okay. So this is kernel 1. So and this we do it for all the 8 registers. So after we do this for all 8 registers, we'll have 8 values per block, right? And each value is a 32-bit, 8 32-bit integer values, right? So we linearize it into 256 values and store it into our global memory. So is this is kernel 1, and after kernel 1 we'll have this sort of data. And to reduce, remember the final goal or final objective was to have it from this input. We wanted to get a 256 array where each value, let's say the 100th value, contained the value 1376. This means that uh, 1376 pixels have the intensity value equal to 100 out of all the 10 out of all the 1000 cross 1024 cross 1024 cross 3 pixels. So in the kernel 2 we just do a simple summation reduction kernel, where we reduce all. So these should remain independent. So we make this dimension independent and do a summation reduction on these dimensions to get the final answer. So I think the key takeaway from this is how to use, if you're uh, if you feel like you are wasting register space, how you can uh, optimally use all bits of a register so that you're not uh, wasting any register space. And also the reason this is important is because the more the number of registers you use, the less is the warp occupancy, and the less optimized your CUDA kernel will be. Yeah, so this is a takeaway from this. I think this has key takeaways. One is how we do this intra block reduction. So how we go from 32 cross 32 into just one value using warp level reduction primitives. This is the first takeaway. And the second takeaway is how we reduce register bit wastage, how we minimize that.